I am Shahid Kumar Dhar. Today I will discuss a problem that came on TIFR 2026 and it's based on metric space or topology. Okay. So it has been said that if x and y be metric spaces and if x to y be a bijective continuous map, then which of the four options are correct? Is or are correct? Okay. Now for this I have to know few things. I am just recalling few things. Okay. Which are the things? These are, what is the meaning of homeomorphism? Homeomorphism means it means continuous plus bijective plus F inverse is also continuous. Okay, these three things are needed to be a function homeomorphism. Okay, now recall this one also. If U be a closed subset of a compact space, it means U is also compact. Okay, note these things also. Under continuous map, a compact subset goes to a compact subset. It's a very well known result. If F is continuous and U is a compact subset, then FU is also compact. Okay, and I have also should know that if X is Hausdorff space, if X is a Hausdorff space and U is a compact subset of X, this implies that U is closed. Okay, it means a compact subset of a Hausdorff space is always closed. Okay, I have to know all these things. I am just recalling this. Okay, now I am starting my main question. You may note it down in your copy. Now here for the first option I have asked if F is homeomorphism or not. F is already given that it is bijection and continuous, so I have to just check if F inverse is continuous or not. Okay, now for this one I just try to check that if S is a closed map. Okay, I'm just for this, let U be a closed subset of, let U be a closed subset of X. Okay, if X is compact, it has given that X is compact, so that's why closed subset of a compact set is always closed. Sorry, it's compact. So I have already written this, that closed subset of a compact set is always compact. That's why U is compact. Okay, now it is given that F is continuous. F is continuous. That's why it implies that Fu is compact in Y, okay, because I have written that under continuous map compact subset goes to a compact subset. So FU is compact in Y, okay. Now Y is metric space, fine. So a metric space is always Hausdorff space, okay. So it is Hausdorff space, okay. Now we have already written that in a Hausdorff space a compact subset is always closed. So this implies that FU is closed in Y, okay. It means this F is a closed map. Now I am telling that Y, it is only necessary to F being a closed map to become F inverse is continuous. I am telling the reason. Now because F inverse is going from Y to X, okay. Now to show it's continuous, I am just taking a closed set from X, okay. Let U be closed in X, okay, and I just want to show function is continuous or not. What we check? We just take a closed set from range set. It is arbitrarily chosen closed set and check if inverse of that closed set in domain is closed or not. If it is closed, then this function is continuous, okay. So I am following this path for this function also. I am taking a closed set from X and I am checking that inverse of that closed set is either closed or not in Y, okay. So my function is F inverse. So F inverse of U, it is, since F is bijection, so if F inverse of inverse will be F, it is F of U, and I have already showed that FU is closed in Y, so it is closed in Y. I have chosen arbitrary closed set from X, and inverse of that closed set is also closed in the domain. That's why this function becomes, it shows that function, what is my function? My function is F inverse, okay. So F inverse is continuous, okay. So my target has fulfilled. My target was to show either F inverse is continuous or not. The two things already given, by F is bijection and continuous. I just have to check if F inverse is continuous or not, and I am showing that F inverse is continuous. So F is a homeomorphism, okay. So first option is absolutely correct. Now I am taking the second, third and fourth options, fine. For the second option, I am just giving a counter example, okay. I am just giving a counter example. Let X equals to and Y equals to S1. It means unit circle in complex plane, okay. Now what will be this? Now for this one I am taking a map F X to Y such that F of X equals to e to the power ix, okay, where x belongs to x, fine. For this reason, this function is very easy. It's a well-known result. It's a continuous function. It's a bijective map also, okay. And here y is compact, okay. This type of circle. this is a circle, just this thing, this is a circle, where unit circle. So unit circle, it is compact in Y, because in a metric space every closed and this Y is compact because it is closed and bounded. Okay, so in a metric space any closed and bounded set is compact. So this is a compact, but does is the set X compact? No, it's not compact at all. Okay, because it is not closed, it is open on 2π, so X is not compact at all. So this option is wrong. Okay, for C, I am taking also a counter example like this. For C, it has been said that it is wrong. For C, if Y is connected, I have to check whether X is connected or not. I am giving a counter example. Okay, let X equals to okay. Okay. Now I am defining a function from the function is from X to Y as usual. Okay, I am defining it as fx equals to X when X belongs to 0, 1, and it's equals to X minus 1 when it belongs to this one. Okay, now this function, you can easily check that it is a bijective function. It's very easy, you can easily check it. It's a bijective function. It's continuous as well, because it's continuous on this interval, it's continuous also in this interval, and I don't need to check at 1 or 2 because it's the boundary point, and these two boundary is not same. Okay, this is 1 and this is 2, there is a gap, so I don't need to check at boundary. Okay, so it's a continuous. Here Y is a 0, 2, so Y is connected as well, it is connected, but X is not connected at all, it's a disconnected set. Okay, so option C is also wrong. I am jumping to the option D. Okay, option D is like, it has been said that if X is R and Y is a subset of R square, then Y is closed. I am also giving a counter example here. Okay, I am taking a map F zeta which is going to R2 f of R. Okay, I am taking Y is a f of R because I can choose it, because Y is a subset of R square, not whole R square. Okay, I am taking Y as f of R. Okay, I have this liberty to take any Y and any X, and I just give with them that a counter example. Okay, now I am making a function such that, sorry, it is f of R. Okay, fine, this which is a subset of R square. Okay, I am making a function such that f of t equals to e to the power t sin t, or I am taking a first time e to the power t cos t, comma e to the power t sin t. Fine, I am taking like this where t belongs to R. Fine, it's a continuous function. Okay, it's very clear because this term is continuous this term is continuous, so this whole function is continuous, okay, because it is term-wise continuous. Now it is also bijective, okay. It easily can be proven that it is bijective because, okay, I am showing it down. Let if t1 equals to f t2, okay, that implies that e to the power t1 cos t1 comma e to the power t1 sin t1, that equals to e to the power t2 cos t2 comma e to the power t2 sin, can be done that. So now do these two components, this component equals to this component and this component equals to this component, and then from this it can easily be sent, it can easily be showed that t1 equals to t2. It's your homework, do this, okay. If not you get into this, then please comment and I will definitely show it, okay. So it is getting by 1 and surjection is already there because f is mapping from R to FR, so its f is from its already by 1 and for bijection I have just have to show surjection, and surjection is already there because f is mapping from R to FR, okay, fine. So f is bijection, f is already continuous, okay, everything is there. I have to show just that y is not a closed set. This mapping from f, this set f of R, it means e to the power t cos t, e to the power t sin t, this such that t belongs to R, this set is not closed, this set is not closed in R square. Can you prove it? It's not that tough, it's an easy thing, okay. Just show that, just see this thing at it is not that tough, it is very easy to show that this set is not closed, because as t tends to minus infinity, this component will go to 0 and this component will also go to 0, okay, as t tends to minus infinity. So this whole component, because e to the power, as t tends to infinity, e to the power t goes to 0, as t tends to minus infinity, e to the power t also goes to 0. So this term, this whole thing goes to 0, 0, okay. So 0, 0 is a limit point of the set, fine, but 0, 0 is not present into the set, but 0, 0 doesn't belongs to into this set, okay. 0, 0 is a limit point of this set, but 0, 0 is not present into the set. So this thing is not closed, okay. I have chosen this as y, I have chosen this as y, well, so it is not closed, okay. So option D is also false. So here is the thing, it's a very beautiful, very conceptual problem that came into the TIFR, okay. So if you like this, please subscribe, like and share and follow. Thank you.